இதில் எப்போ ஸ்க்ரீன் ஷேர் பண்ணுறது? அவங்க கொடுக்கணும்ல
ஆமா ஆமா அவங்க கொடுக்கணும்
ஆப்ஷனு.
ஆமா
அவங்க ஸ்க்ரீன் ஷேர் பண்ணக்கூடாது தான் வரும்.
ஆமா அதுதான் அப்படி.
Good morning, sir. Shivaraman, sir. Sir, good morning, sir. Yeah, you joined, sir. Just actually here, you're connecting, sir. 2 minutes, sir. 2 minutes, sir. Be online, sir. Just two ports are there for this system. Here only, master. This side only we have both. Sir, Good morning, sir. Sir, good morning, sir. Are you able to hear me?
Good morning, sir.
Yeah,
Yes.
good morning, sir. Sir, actually, we are connecting one system. It is not working. In 2 minutes
Okay.
we'll start, sir. Yeah.
Shall we begin, sir?
So now I'm audible, sir. Yeah, 2 minutes, sir. 2 minutes, sir.
Okay.
Just we are connecting here system, sir. Just 2 minutes. So this is the offline and online, sir. That's reason. At a time we are showing offline to the students. So we are connecting, sir. 2 minutes be online. Sir.
So can you hear us?
Yes, I'm.
So can you hear us?
I'm hearing you, sir. Yes, yes, yes. I can hear you, sir. No problem.
Yes, sir.
We'll start the session.
Good morning, all. I'm Nagalakshmi, Coordinator, Alan Turinka. Welcomes Reverend Brother Vincent Reddy, Principal, LFDC, Mrs. Jayanti Reddy, Vice Principal, LFDC, and today esteemed speaker of the day, Mr. Dr. R. Shivaraman, Associate Professor, DG Vaishnav College, Chennai, and also founder of Pi Mathematics Association. Respected faculty members and dear students, I now call upon Mr. Mohammad Saif, first BSc MSCA student, to lead us into prayer.
Heavenly Father, we thank you for this pleasant and beautiful day that you have made. We thank you for the life and lives of our beloved ones. We thank you for your presence in our lives and the confidence we have in you and the plans you have for us. We especially today pray for our Dr. R. Shivaraman, who is in our midst. Bless him, Lord, with your knowledge and wisdom, so that he can enlighten us with his experiences. Bless us with your abundance of love and wisdom, so that whatever we grasp and understand would enable us to transmit and transform the lives of whomever we meet every day. Amen.
Thank you. Please be seated. I have called upon Mrs. Swapna, Department of Mathematics, to please introduce our guest speaker.
Good morning, one and all. It's my immense pleasure to introduce today's speaker, Dr. R. Shivaraman. Dr. R. Shivaraman, currently working as Associate Professor of Mathematics, has more than 20 years of teaching experience. His areas of interest are number theory, real analysis, and applied mathematics. He has published more than 30 research papers in various international journals. He has successfully guided 6 MPhil students. He is reviewer of editorial board member for 10 international UGC approved journals in mathematics. Has been involved as resource person in training teachers appointed by Teacher Recruitment Board, RMS and SSA. Has been conferred with Honorary Doctor of Letters from California Public University, American Honorary Doctor of Science from University of Swahili, Republic of Panama, Central America. He secured 15th All India rank combined category conducted by CSIR. He has secured All India 27th rank in the Graduate Aptitude Test for Engineering exam conducted by IIT Madras with a percentile score of 96.3. So has been conferred with National Award for Popularizing Mathematics among Masses in 2016 by Department of Science and Technology, Government of India. It was conferred with prestigious Indian National Science Academy Teaching Award for the year 2018. This award is the greatest recognition for teacher working in college or university throughout India. He has also received 2 state government best book awards in science for consecutive years 2011 and 12. So far, Sir has received 9 Best Book Awards for the 15 books written for disseminating mathematics and science. Among these 15 books, 10 were in Tamil and 5 in English. He has received Abdul Kalam Teaching Excellence Award in 2015 and Abdul Kalam Scientific Excellence Award in 2017. He was overall won more than 20 prestigious awards for his contributions to mathematics so far. Sir has provided more than 3,000 lectures throughout India, conveying the beauty and importance of mathematics and its applications. Spreading mathematics among everyone was his life vision. He is life member of the prestigious mathematical organizations like American Mathematical Society, London Mathematical Society, Indian Mathematical Society, Ramanujan Mathematical Society, and Mathematics Teachers Association. He is a founder, trustee of Pi Mathematics Association, and academic secretary of Association of Mathematics Teachers of India. He is currently editor of the journal Junior Mathematician, a quarterly magazine for school students published by AMTI. He was a member of a team appointed by State Government School Education Department for preparing 100 mathematical models for 100 corporate schools in 2008. He was also a member of Textbook Writing Committee, Tamil Nadu School Education Department for preparing revised mathematics text for 11th class new syllabus. He is a chairperson of the 10th class new mathematics textbook released in June 2019. He won 3 Distinguished Teachers Awards so far. He was a recipient of more than 30 Distinguished Awards for his wide contributions to mathematics. He writes regular articles and provides puzzles for famous newspapers like the New Indian Express, Times of India, Hindu School Edition paper, the Dinamar Pattam newspaper. He has also contributed several articles about mathematics in monthly magazines like Chutti Viketan, Manjari, Arabiya Lolly, Chennai Report, Arambu, and continue to do more. Little Flower welcomes you, sir, for this session.
Thank you, Swapna ma'am, for that warm introduction. I once again invite Professor Shivaraman sir and would request him to take over the session.
So thank you for this introduction. So I'll straight away begin my session. Is the screen visible to you?
Yes, sir.
Yes, sir.
Okay. So first, I let my thanks to Little Flower Degree College, Hyderabad, and my dear friends and colleagues in the Department of Mathematics. I think there's some echo in the room, sir. Can you rectify it? Okay. So
Yes,
shall I
sir. We are trying
continue?
to do it, sir. We are trying to do it, sir. Still, you have
Okay.
an echo, sir.
Okay.
Still,
So
you have an echo, sir.
the topic of the talk is glimpses of Srinivasa Ramanujan. The best way, of course, to remember Ramanujan was to look at his mathematics because he lived his whole life for the cause of mathematics. So I will be discussing few aspects, in fact, not deeper aspects, but some of the basic aspects of mathematics done by Ramanujan. The voice visible, I mean, clear to you, sir? Shall I continue?
Yes, sir.
Sir, your voice is audible, sir, and it's clear, sir. Please
Okay,
continue, sir.
thank you. So, this is date of birth magic for Ramanujan, but I can tell you that it was constructed not by Ramanujan but by me because it contains today's date. You see, 4/2/2021. 4/2/2021 is here. Today's date, and today's date is very special. I don't know. It so happened that we have chosen this particular date, which is very interesting actually in number theoretic aspect, because 4, 2 are two numbers which satisfy a wonderful property. They are the only numbers to satisfy the form a power b is equal to b power. That means regarding integers. With respect to positive integers, there are only two numbers, 2 and 4, which satisfy the condition that a power b is equal to b power. That is 2 power 4 is equal to 4 power 2. If you change base and power, the answer would be same. Amounts to 15. So that's one of the curious things that you find with today's date. And this magic square is constructed by me, where the first row contained date of birth of Srinivasa Ramanujan. He was born on 22nd of December 1887. Now, I can tell you most of the literature claims that this kind of magic square was very much circulated in the internet, where the first row contains Srinivasa Ramanujan's date of birth, and it was said, claimed in other sources that this kind of magic squares were constructed by Ramanujan himself, which is untrue. In fact, at the end of the lecture or this talk, I will highlight some part of that. So we will straight away begin our main part of the talk. Now, if you look at this square root problem, this was constructed by myself in the spirit of how Ramanujan did in his notebook. If some of you or one of you can guess this answer, what I'm trying to manipulate this, what could be possibly answer for this, that will be better. Anyway, you can ask your doubts if you have any at the end of the talk. This photograph was my one of the very favorite photograph, because Ramanujan did great works in number theory, and this portrait of Ramanujan was constructed purely using only numbers. I hope I have shown this when during my talk during last year when I came to your college in offline mode. I have shown this picture if I remember. So those who attended that lecture can remember. Now see, the eyebrow, the number starts here 1, 2, 3, 4, 5, 6, 7, 8, and it continues on and on like this, and it ends with 500. This is 499, 500. This is collar of the shirt. So this whole picture was created using first 500 natural numbers. This was created by one of my friends, J. Prabhakar, and he gave this as a gift for publishing in my book when I was writing in 2012. That book, Engali Nanbar, a big volume book up to 450 pages, was considered to be one of the good books in Tamil, written in Tamil, for describing life and work of Ramanujan in much detailed fashion. In fact, that is one of the two books that was mentioned which got Best Science Book Award from Government of Tamil Nadu during the introduction of. And this is where Ramanujan was born. Ramanujan was born at his maternal grandmother's house. This was located even today at E Road, Aragia Singer Street, or something like that. And this news was published in the Hindu newspaper in Metro Plus column. You can see the date February 26, 2013. So nearly 8 years back, this particular news was published. This is where you can go to Google and check. If you just type this word, you can search, you get this news. So you get the details of the home where Ramanujan was born. It is still there. Okay. So let us go to the main part of the uh, fact that, as I told before, Ramanujan was today remembered most part for his mathematics. So we'll begin with some of his basic mathematics and slightly increase the level as we progress. So if you take these two equations, root x plus y is equal to 7 and x plus root y is equal to 11, what could be the values of x and y? When this was asked, this problem was posed to Ramanujan when he was a young student by his 1 year senior, where Ramanujan was in fourth form, which is around maybe some sixth class or something like that, sixth class or seventh class or something. And this was posed by his senior schoolmate, C.V. Rajagopalachari, who was 1 year senior to him. He was in the next form, fifth form. Rajagopalachari thought Ramanujan would take more time to solve this, but for Ramanujan's genius, it was very easy for him to solve. He immediately gave the answer that x is 9, y is 4. As you can check here, if you put x is 9, this is square root of 9, that is 3. 3 plus 4 is 7. And this is 9 plus root 4. Root 4 is 2, so 9 plus 2 is 11. So this is not a very difficult problem. The solution is given in detail. This kind of solution will be done in usual classes when you are asked to solve. But one thing I guessed how Ramanujan could have done this is, because there is square root of x and square root of y terms, it was very clear that x and y are perfect squares. If you want solution in terms of integers, positive integers, then it is certainly true that x and y should be perfect square. So it's not very difficult to check out the perfect squares. It turns out that x should be 9 and y should be 4. In that case, you get this answer. So it would have taken less than a minute, maybe few seconds for Ramanujan to guess this. He was master in guessing the solutions to such puzzles. Now, if you are given 18, when he was again a student of young age in his class, the teacher was teaching division process, and he was teaching like this. This is just a sample. He may not have done the same thing. It's just an example, especially for school students to understand. So there are 18 things with you, objects with you. You want to split this 18 objects to 3 people such that each people will have same share of objects. In that case, the whole 18 objects can be shared to 3 people with 6, each getting 6 of them. And that is why if you divide 18 by 3, you get 6. So this is division process. In other words, division is equal sharing. The process of division is simply equal sharing. If you have so many objects with you, and if you want to split them into, say, some number of people, say 2 or 3 or 4 or some number of people, such that each receive the same amount of objects, then that process is simply division. So I have 18 objects here, and if you split them to 3 people such that each of them get equal share, then each of them would get 6 then, because of the fact that 18 by 3 is 6. Similarly, there are 12 cups of cupcakes here. You want to distribute 12 cupcakes to 3 persons such that each would get same amount of cupcakes. In that case, you get the condition that if you split this into 3 parts, equal parts, you get 4 each. So each person receiving this 4 cups of cupcakes to their share, and therefore this explains the fact that 12 divided by 3 is 4. So the number of objects that each person would get actually gives the answer for the division. That is the quotient of the division. Okay? If something is left out, that will be the remainder. And of course, here there's nothing, no objects are left out. We have chosen in such a way that it can be split equally without any remainder. Okay. Now, I have some 6 bananas I want to share with 2 students. So I can give 3 bananas to each student. So these are all simple examples of sharing objects to people with equal share. So that how many would each would get, that gives the answer for the division. Now when teacher was telling that, so if you have 10 apples with you and if you want to share with 10 people, how much would each get? People said that students in the other class students said that each would get 1. So teacher explained that if you have number of objects and number of people if this count are same, then each would always get 1. That explains why if you divide a number by the same number, that is, if you take a number x and divide by x, you get 1. So if the number of objects and number of people to get shared are equal, then each would get only 1. So that explains the basic fact that any number x divided by x if it is always 1. Then Ramanujan raised his hand and asked, "Sir, I have a doubt that if there are no students and no person to share, would still each would get 1?" The other students, his classmates, immediately laughed at him because, see, logically this question has no meaning, because if there are no objects with you, say no fruits or no cakes to you with you, there's no point of even thinking of sharing with others. If there's only at least one or two things with you, you can try to share with others and even think of it. So the question itself seems to be illogical, but what Ramanujan was thinking was a very deep question, actually speaking. He was thinking about a basic question from differential calculus. That was his mind reach. He was thinking about so much of higher ideas even in his lower class. Ramanujan was asking, what is 0 by 0? If teacher could say, if any number divided by the same number is 1, still 0 by 0 becomes 1. This is what Ramanujan was trying to ask. Now, as you can see, 0 by 0 is one of the 7 indeterminate standard indeterminate forms. 0 by 0 is not neither 1 nor 2, or 0 by 0 in fact can be any number as you like. So it is considered to be one of these indeterminate forms. So it has no specific answer. So this was actually what Ramanujan, this far Ramanujan could think even at his young age. So this is a very classic example of how Ramanujan, even as a young boy, could think very deeply. Now, if you look at the notebooks of Ramanujan, in the first chapter, there was he began with what is called the magic squares. This is the first page of Ramanujan's notebooks. He has written 3 notebooks so far, and in the first page you can see a magic square. This is one handwriting of Ramanujan. You could have constructed a magic square like 1, 2, 3, 4, 5, 6, 7, 8, 9. The first 9 numbers are used here. Now, the magic square is a simple construction of a square array with numbers such that each row and each column and leading diagonals will always add up to the same number. That same number is usually called the magic sum or magic constant or whatever it is. So here in this case, 6 plus 1 is 7, 7 plus 8 is 15, 7 plus 6 is 7 plus 5 is 12, 12 plus 3 is 15, 2 plus 9 is 11, 11 plus 4 is 2 plus 9 is 11, 11 plus 4 is 15. So each row would add up to 15. Similarly, you can check that each column would add up to 15 and each diagonal would add up to 15. For diagonals, you see 6 plus 5 is 11, 11 plus 4 is 15, 2 plus 5 is 7, 7 plus 8 is 15. So if sum of each row, each column and 2 leading diagonals would add up to the same number, such a construction or such a square is called a magic square. Now the constant, the same answer that you get is called magic constant or magic sum or whatever it is. 15 is the magic sum for this particular magic square. And here in the second magic square, you could have used only odd numbers like 1, 3, 5, 7, 9, 11, 13, 15, 17. You could have used the first 9 odd numbers to construct the second magic square. Here the magic sum, as you can see, would add up to 27. Now I was wondering, why could he choose this particular magic square of and constructing with odd numbers, and does he have any significance with the number 27? In fact, in most of the cases, Ramanujan, if he does something, he could have had a big meaning behind it. In other words, he could not do anything randomly, unless otherwise it has a specific meaning or specific advantage in it for later period. He could not write it in his notebook. So everything is done for a specific reason. And maybe I don't know the exact reason for why Ramanujan wrote this, but according to reading his mind, I think that this magic square is constructed to get magic sum 27 because he was very good at astrology and applications of all these aspects in numbers to real life situations. Like he could speak more, connect properties of numbers with real life situations. So in that sense, if you see, the magic sum 27 specifies the number of stars of birth, like Uttarataji or Purataji, whatever you call. There are 27 primary stars of zodiac signs and 12 symbols specifying the rasis, and nakshatras, there are 27 primary nakshatras, and probably to signify that importance, probably could have constructed. That's only a guess. I'm not sure about it. But I was also wondering, magic square construction was a very old thing. It's not new. It was not introduced by Ramanujan. Magic squares was known to humanity some 2000 years ago, even before the period of Ramanujan. So why could Ramanujan could have chosen such a playful thing? Because he was considered to be a mathematician who had done very, very deep mathematics. Of course, this was written by him when he was very young age, not as a scholar or with 30 years or 40 years of age. Remember, he died at the age of 32, very young age. So this work, just jotting and inscription, was made by Ramanujan in his notebook when he was probably a school student with not much of age. But even then, Ramanujan's given Ramanujan's caliber and deep thinking, this is a very, very playful way for him. But I was thinking why could have chosen this. But then after some investigation and after some years, I got the answer, because he understood that if you add the row sum, like 6 plus 1 plus 8, first row and third row, if you take first row and third row, 6 plus 1 plus 8 is equal to 2 plus 9 plus 4, both adding up to 15. But not only that, he found that if you square and add, you get the same answer here. So in this case, you get 101. 6 square, the same numbers, I'm adding as it is, and I'm squaring and adding it. So 6 square plus 1 square plus 8 square will be same as 2 square plus 9 square plus 4 square. Similarly, if you take the first column and the third column, you get 6 plus 7 plus 2 is equal to 8 plus 3 plus 4. If you square and add this, you get 89 on both sides. This is 89 and this is 89. So I was wondering how Ramanujan could even guess this thing, see, even he was very young age. So a same construction giving multiple solutions. This was one of his chief characteristics. I mean, he not only can find a single answer, but with this work, with the same problem, with the same solution, he could get multiple answers. Not only addressing the given problem, but also for different problems also. So there is an additional feature that you find in Ramanujan's work very often. So other good example, basic example of Ramanujan thinking was here. If you add 1, 1, 2, 6, you get 10, and 3, 3, 4, you get 10. So not only they add up to the same number, but if you raise them to the same power and multiply, like 1 power 1, 1 power 1, 2 power 2, 6 power 6, that will be equal to 3 power 3, 3 power 3, 4 power 4. So you see, so they are not only true with respect to addition, but also power multiplication, where each power is raised to the same number. Like if you have 2 here, raised to the power 2. Any number is raised to the same power. Therefore, even in then you get this answer. There's no difficulty in seeing why this is true, because if you write 6 power 6 as 2 power 6 times 3 power 6, because 6 is 2 times 3, and count number of 2's in the left hand side and number of 3's in the right hand side. This is 2 power 2. This is 2 power 6 into 3 power 6. The 3 power 6 is obtained here. 3 power 3 into 3 power 3 is 3 power 6. So I have 3 power 6 here. This is, you get 2 power 6 here and 2 power 2 here. They add up to 2 power 8. 2 power 8 is equal to 4 power 4, because 4 is 2 square. So if you write 4 as 2 square, this is 2 power 8. You have 2 power 8 here. And you have 3 power 6 here, 3 power 6. So they are equal. Okay, you don't need to multiply and verify this answer. So count how many 2's here and count how many 2's here, count how many 3's here, count how many 3's here in the product. If they are equal, then the product is equal. Similarly, if you take this expression 1 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6, they add up to 15. And if you count this also, you get 50. So not only they are equal in addition, but if you raise to the same power, again, you get the same answer. So this was one of the beautiful things that you can find in Ramanujan's work. Okay, so here you can see 1 plus 4 is 5, 5 plus 25 plus 30, 55. If you add the numbers, the 6 plus 24 is 30, 30 plus 25 is 55. So both ways, if you add them, you get 55. As well as if you multiply by taking the same power, you get the same answer. So this will not be true for all collection of numbers. You have to choose very specific numbers. Only then it will work. Now, in today's scenario, computer scientists will just plug in programs and they write programming languages to look out for churning out numbers with this property. It's not very difficult task nowadays, especially when you have such computing powers, machines. which can do these calculations and provide the answers within few seconds. But in Ramanujan time, nearly 120 or 130 years ago, when he was doing this, it was not so easy. I mean, I wonder how Ramanujan could even think of such beautiful identities. See, not only Ramanujan's formulas and equations are true, but they have a hidden beauty and wonderful aspect behind them. You have to have a special idea to look how beautiful the formulas are. That is one of the main thing that you get when looking at Ramanujan's work. So here, if alpha square plus alpha beta plus beta square is 3 lambda gamma square, if this condition, if you choose numbers alpha, beta, lambda and gamma satisfying this identity, then Ramanujan wrote this cube plus this cube, sum of these two cubes is equal to, this is equal to sign, this is equal to sum of these two cubes. In particular, if you take alpha 3 beta 0 gamma 1 lambda 3 here, if you take alpha 3 beta 0, because beta 0, this becomes 0, this becomes 0, alpha 3, so left hand side will become 9, alpha square is 9. What about right hand side? 3 lambda, 3 times lambda is 3, gamma is 1, gamma square is 1 here, so this is also 9, 3 times 3 is 9. So if I have chosen this kind of constant satisfying this equation, then I can plug in this here. So you see alpha plus lambda square gamma, alpha is 3, lambda square is 9, 9 into 1, 9 into 1 is 9, so 9 plus 3 is 12, so this is 12 cube, this is 12 cube, beta 0, so whatever lambda might be, this is 0, gamma is 1, this is 1 cube, so 12 cube plus 1 cube is equal to, if you take the right hand side here, this is lambda alpha plus gamma the whole cube. Lambda alpha is 3 times 3 is 9, 9 plus 1 is 10, so this is 10 cube, and if you look at beta 0 here, lambda square gamma, lambda square is 9, gamma is 1, so this is 9, so this is 10 cube plus 9 cube, so you get 12 cube plus 1 cube is equal to 10 cube plus 9 cube. In fact, 1729 is what you get when you add them. So 1729 is very famously called Ramanujan number. It's the smallest number which can be expressible as sum of two cubes in two different ways. Now mathematicians have generalized this concept into what is now called a taxi cab numbers, where they find numbers like sum of three cubes in two ways, sum of three cubes in three ways, and all those things. You can construct sum of fourth powers in two ways, sum of fourth powers in three ways, and all those things. And they know how, when the numbers exist, when this does not exist, and all those things. So such kind of generalizations are usually now called taxi cab numbers because of the incident of Ramanujan's story, which I'm not going to do here. So in fact, there are 4 or 5 such occasions in Ramanujan's notebook where Ramanujan could have written this kind of equations leading to the answer 1729. So not just at one place, but at least at 4 or 5 places Ramanujan could have written such identities. And these identities are called conditional identities, because the sum of these two cubes is equal to sum of these two cubes is not true for any numbers, but only if they satisfy this condition. So only if the chosen constant satisfy this condition, sum of these two cubes is equal to sum of these two cubes. So this type of conditional identities were found in many parts of Ramanujan's work, especially when he was very young. He could generate all such things. So many people think that whenever Hardy said 1729, Ramanujan, some by magic, he could tell the property that it is sum of two cubes on two ways. It is not by magic, but because of hard work and severe practice. When Ramanujan was young, he knew this formula. He could have calculated this constant, and he knew the fact that 1729 is the smallest number to be expressible in this way. It so happened incidentally that Hardy gave the same number which already Ramanujan knew very well, and therefore he could mention that property. Now many people would think that Ramanujan could do because he is having the blessing of his family deity Namagiri Tayar, and she was blessing him with all mathematics knowledge. Only because of that Ramanujan could do such magic with mathematics. But it was not so. See, though he was blessed with great knowledge in mathematics, he revealed that knowledge to the world by his hard work and patience. He devoted his whole time for the cause of mathematics. He never went outside with his family. He never had any enjoyable time. He always thought about mathematics and devoted his full time to the research in mathematics. Only because of that devotion and dedication and hard work in doing research and doing this kind of formulas, he could reveal his genius. Sometimes people may be blessed with many great things, but unless they work very hard and they dedicate, they can't realize their potential. So this is one of the main lesson that you can learn from Ramanujan's life. Okay. So this is another conditional identity. So as I told you, he was making so much of conditional identities in his notebook. I'm not going to explain in brief because I want to cover certain important things. So if A by B is equal to C by D, then he could have written sum of this 3/4 powers is equal to sum of these 3/4 powers. A plus B plus C the power 4 plus B plus C plus D the power 4 plus A minus D to the power 4 is equal to C plus D plus A. See the symmetry in the equation. C plus D plus A the whole power 4 plus D plus A plus B the whole power 4 plus B minus C the whole power 4. And very interestingly, as I told you, in many cases Ramanujan was a multiple task master, in the sense that he not only was producing one formula, but the same formula he could generate to use to generate other formulas also. So in that sense, you have written a marginal note here saying that in this 4 may be replaced by 2 also, which means this formula will become true even if you replace 4 by 2. That is, if you replace 4th powers by squares, even then some of these 3 squares will be some of these 3 squares. You could have given many examples. See how much time he could have taken to generate all such work and doing all these calculations. You see, it could have taken at least few hours for him. As a young student, of course, not as a when he was above 15 years or 20 years. By then he was very much thinking very quickly, but he did this as a young student around 10, 12 years or 13 years or so, not very old. Okay. Ramanujan started publishing questions to IMS, Indian Mathematical Society, which published a journal for its members. Indian Mathematical Society is the first mathematical society to begin in India in 1907. And Ramanujan was the founder was very much helpful to Ramanujan in helping him to publish his discoveries in the journal of IMS. And in one of the issue of the IMS journal, these 2 problems were posed by Ramanujan. It is the problem question number 289, in which Ramanujan posed these 2 problems: square root of 1 plus 2, 1 plus 3 root of 1. Most of you could have seen these problems, and any person who talks about Ramanujan could have quoted about these 2 problems. I'm not sure about how many of you know, but for the sake of beauty of this,
sir, sorry to interrupt you.
Yes.
Sir, sorry to interrupt you. Some of the slides are very small. Can you just zoom a little bit so that the students can, those sitting at the back, they are not able to see that?
No, actually, I have maximized my screen. This is the maximum possible thing that I can do.
No, some of the texts are very small. Okay,
No,
okay, right.
I don't think I can help in this, but anyway, I can share maybe later. If they can listen and write down, if you want, I can share them.
Yeah, fine.
Okay.
You
So
can continue, sir. Yeah.
Yes, these are the 2 problems posed by Ramanujan in the journal of IMS, as I told you. It happened that none of the person could give the solution when after Ramanujan posted this. It became around 3 months. The editor was waiting to get solution from some person who could solve this, but unfortunately none could solve. This was around 1908 or 1909, that period, near to that period, some 110 years ago. So none of them could solve this puzzle. So what happened was the editor wrote back to Ramanujan asking him to provide the solution himself. And Ramanujan was very trickier, he was very mischievous in this aspect. Like he gave the answer for the first problem as 3 and gave the answer for second problem as 4. I was actually flabbergasted to see this answer in the first instance when I saw this problem as a young boy, because you see there are so many square roots and there are infinitely many square roots, what we call nested radical problem. See, if you have a square root or cube root, it's called radical sign, and there are infinite radical symbols that you find here. Even a single square root radical number like root 2, for example, cannot be written as an integer like 3 or 4 or something. It cannot be even written as a fraction of two integers. Like it's not equal to a rational number put in the form p by q. So even if a single radical sign cannot be returned very nicely, how could Ramanujan can think of writing so much of infinite radical symbol and getting a nice answer as 3 or 4 like this? This is quite remarkable. I mean, that is why probably the biography written about Raman, best known biography, was titled "The Man Who Knew Infinite," because he knew the causes of numbers or identities which can go up to infinity, and he could explore such infiniteness and can come up with a nice answer, like a very good answer like this. So it's a very apt title that Ramanujan was termed as the man who knew infinity. It doesn't mean that he had given the properties of infinity, but he knew the properties of infinite radical signs or infinite square root signs, infinite cube root signs, or infinite integrals, or infinite derivative terms, or infiniteness. He could handle infinites with very ease compared to other mathematicians. In that sense, he was claimed like that. I have given a solution. Many sources claim that this solution was provided by Ramanujan himself. That is untrue. Again, there was some false interpretations about Ramanujan's work and life. So I'll be discussing, I mean, whenever possible, I would tell you. Then if you see a source that this proof was given by Ramanujan, that is not true. Ramanujan's proof was not this. This was done by some later mathematician. Okay. So just to explain to people, you see n plus 2 whole square can be written as n square plus 4n plus 4, which I can write as n square plus 4n plus 3. 4 is 3 plus 1. I can write this 4 as 3 plus 1. Now, is the screen visible, sir? To students? Hello?
Yes, sir.
Okay.
Yes, sir.
So this 4 is written as 3 plus 1. You keep this 1 as it is and factorize this term, n square plus 4n plus 3 as n plus 1 into n plus 3. So this term can be factorized as n plus 1 into n plus 3. So this is n plus 2 the whole square. So n plus 2 whole square is 1 plus this. So n plus 2 becomes square root of this. Root of 1 plus n plus 1 times n plus 3. And you multiply by n on both sides. You get this expression. I'm going to take f of n as this symbol. So the left hand side is f of n. F of n I'm going to assume as n into n plus 2. The above relation, then this is f of n for me. Because this is f of n is n times. What is f of n plus 1? See, if f of n is n into n plus 2, f of n plus 1 will become n plus 1 into n plus 3. You will increase n by 1. So if f of n is n into n plus 2, f of n plus 1 will become n plus 1 times n plus 3. And that is what you find here. So I can write this as f of n plus 1. This n plus 1 into n plus 3 will become f of n plus 1 because f of n is n into n plus 2. Okay. So this is f of n. I can write f of n here. This is n into square root of 1 plus. This is f of n plus 1. So I can apply this formula again because f of n now is n into root of 1 plus f of n plus 1. I wrote this again, as it is. Now apply this formula. What is f of n plus 1 now? F of n plus 1, if you replace n by n plus 1 here, then you get f of n plus 1 is n plus 1 into root of 1 plus f of n plus 2. And again apply f of n plus 2 is n plus 2 into root of 1 plus f of n plus 3. And f of n plus 3 is n plus 3 into root of 1 plus f of fn plus 4. And we keep on replacing this identity by increasing 1 each time recursively. What you ultimately get is this. And f of n, remember, is n into n plus 2. So if you replace f of n here as n into n plus 2, I can cancel this n on both sides. So this expression is n plus 2. So if you put n as 1, the left hand side becomes 1 into 1 plus 2. 1 into 1 plus 2 is 3. Left hand side becomes 3. Right hand side becomes 1 into 1 multiplied by anything is the same number. So don't bother about this n because n is 1 here. And if you substitute the n value here in the inside the radical sign, you get 1 plus 1 is 2. So you get 2 here. This n plus 2, n is 1 here. So this is 1 plus 3 now. And this is 1 plus 4. Next term is 1 plus 5. So you get this problem. So this is a solution. That's how you get 3 for this first problem. And similarly, if you can do this calculation by taking n plus 3 whole square rather than n plus 2 whole square, if you consider n plus 3 whole square and group the terms and assume f of n is n into n plus 3 and applying the formula recursively, you get this answer. Now, once you know this, and if you put n as 1 in the final answer, you get 1 into 1 plus 3 is 4. So you get 4 in the left hand side. This n is 1 here. You substitute n is 1 here, you get 1 plus 5 is 6. 1 plus 1 is 2. 1 plus 6 is 7. 1 plus 2 is 3. So you get, and the nice thing about this formula is you can see 6, 7, 8, 9. The first numbers are consecutive numbers beginning with 6, 6, 7, 8, 9, 10, etc. The second numbers are 2, 3, 4, 5, 6, etc. So you get some nice pattern. So not only that you have nested radical formula, but the terms inside the nested radical sign, each of them behaves with a very nice pattern. So this is one of the remarkable things that you often find with Ramanujan's mathematics. You see, and the guess to the answer. There is a special thing that you can find in the answer. In the first case, if you add these two numbers, listen. If you add these two numbers, 1 plus 2, you get 3. So if you find any such problem of this type, this particular radical symbol type, sum of these two is the answer. 1 plus 2 is 3. And here, if you take average of these two, 6 plus 2 is 8, 8 by 2 is 4. In other words, the answer lies between these two numbers. It is so this number is 2 more than this, and this number is 2 less than this. In other words, the answer here is average of these two numbers. So keeping this in mind, if you look at the first problem that I posed, this is of the second type. The second problem type, that instead of beginning at 6, is it visible now? The first screen?
Yes, sir.
So I think there is someone disturbing. I mean, why the disturbance is coming?
Sir, we just lost connection for a moment, sir. So we couldn't hear you. We sorted out. Now it's fine, sir.
No, shall I repeat them?
Yes, sir. Yes, sir.
Should I repeat?
No, sir. Only last slide a little bit. Just
Okay.
1 minute, sir.
Okay, no problem. So this particular puzzle that I have constructed here, I told you this constructed in the spirit of Ramanujan's work. In fact, this puzzle was constructed in the spirit of second puzzle posed by Ramanujan in Journal of IMS. So the answer to this is average of these two. So if you add these two, you get 266, and dividing that by 2, you get 133. So this first number is 2 more than that, and second number here is 2 less than that. As you can see here, this answer here is this 4 is, this first number here is 2 more than that, and second number is 2 less than that. So in other words, the average of 6 and 2 is 4. So similar to this, if you look at the puzzle that I posed, the first number is 135, second number is 131. So the average of 135 and 131 is 133. That should be the answer for the puzzle that I posed in the initial screen. And what is that to anything to do with 133? 133 is Ramanujan's age as of today, because I told you he was born in the year 1887, December. So he could be 133 years as of now. And so the puzzle gives the age of Ramanujan as of today. You can even construct, for any number, you can construct such nested radical sign. Now, what actually Ramanujan was trying to do was, he in the chapter 12 of his second notebook, he could have written this gallery of formulas. Okay, and if you look at probably the fourth formula in the list, this is x plus n plus a, the square root of ax plus n plus a the whole square. This is the fourth formula in the list of several formulas in this chapter 12 of his notebook. Now, this is the more general formula that Ramanujan had up his sleeve. So he was having this and hiding this general formula and not revealing this to anyone. Okay, what he did was he had substituted x is 2, n is 1, and a is 0. If you substitute this here, you get this puzzle. If you put x is 2, n is 1, and a is 0, you get 2 plus 1 plus 0, that is 3. So he was giving only the special case, not the general case. He knew even in many integral problems, he knew the general integral answer. He used to tease others by posing special cases. Now people got utterly confused in solving, and even if they could solve only few of them because they could not know the general form of what Ramanujan was thinking. So in that sense, Ramanujan was always playing with others by keeping the more general thing with himself and revealing only the special cases. So this is one of the things. This is actually from Ramanujan's work. So this is original Ramanujan work. Okay. So I will probably highlight two puzzles. One puzzle I will discuss in detail. The other puzzle I will just give it to you. I have given the solution also, so that people may get some taste of how Ramanujan could have thought. Okay. Um, there was an incident in 1914 December when Ramanujan was beginning to do his research at England. He went to England by April of 1914. Around 6 or 7 months since he was there, he became friend with another Indian statistician who was called father of statistics in India, and he is founder of what is called the Indian Statistical Institute (ISI), which is one of the premier institute for statistics even today. He was founder of that institute. His name was Mahalanobis. Mahalanobis became very close associate of Ramanujan when both were at England. Uh, he was visiting Ramanujan's hostel room during one Sunday morning, and there was a magazine which was published called Strand magazine, which contained interesting puzzles like this one. This is the original page of the Strand magazine puzzle. Uh, I thank my friend who shared me this some years ago, this original puzzle book. So in that, actually, this is the page of the book, okay, that Strand magazine book. So I will just explain. There was a puzzle which actually Mahalanobis could solve only for the first case, but he could not know the full answer. So he was trying to seek help of Ramanujan to get solved that puzzle. Ramanujan was making the breakfast ready. He was just uh, preparing things for their breakfast for himself and his friend Mahalanobis. He was just doing something in the stove when Mahalanobis approached him and mentioned this puzzle like this. This was the puzzle. He said the house of his friend was in a long street numbered on this side 1, 2, 3, and so on, and that all the numbers on one side of him added up exactly same as all the numbers on the other side of him. Funny thing that he said he knew there was something like that. So the idea is this: there was a long street in which on both sides of the street there were houses. On one side of the street, the houses were numbered like 1, 2, 3, 4, as in the usual street that we live even now. So it so happened that you want to find location of a house number. That is the thing. I don't know how he had done it. Perhaps the reader may like to discover the number of that house. So the puzzle was asking to find the house number such a way that if you add all the numbers before that house number, that will be equal to sum of all the house numbers after that in the other side of the street. Like supposing if there are 10 houses on one side of the street, if you add 1 to 9, that will be equal to sum of next number, like the number after 10 is 11, sum of 11 to 20 or 25 or something like that. So there are, out of total number of houses in the street, if you add from 1 to, I will explain this here, if you add 1 from, so supposing that the whole street contains m number of houses, the puzzle is asking you to find house number n such that if you add all the houses up to n minus 1, the one previous to the required house number, the house number is n. What I want to find is house number n out of m houses in the street. So naturally m is greater than n, such that if you add house numbers before n, that is up to 1 to n minus 1, that should be equal to after n, that is n plus 1, n plus 2 up to m, because there are totally m houses. So I want to find n such that the sum of numbers previous to n is equal to sum of numbers after n up to the total number of houses, say m. This is what the puzzle is asking about. Now Mahalanobis could easily guess the first answer to this, but he could not solve this because the puzzle was stating a condition that he said he knew there was more than 50 houses on that side of the street, but not so many as 500. That is, the number of houses, total number of houses on the street on either side is between somewhere between 50 and 500. So this restriction was given, and Mahalanobis solution was not satisfying this restriction. Therefore, he could not solve the problem, and that is why he was seeking Ramanujan's help. So you can see here, if you add 1 up to n minus 1, this by usual form you could have studied in 10th class or 9th class in your high school, that sum of first k natural numbers is k into k plus 1 by 2. So using that here, 1 plus 2 plus up to n minus 1 is n minus 1 into n minus 1 plus 1, the next number, which is n by 2. Usual summation formula. And if you can write this n plus 1, n plus 2 up to m as 1 up to m minus 1 to n. So write this sum as 1 plus 2 plus 3 up to n plus n plus 1 plus n plus 2 up to n minus 1 up to 2 up to n. That is, you add and subtract the quantity 1 plus 2 plus up to n here. So if you add 1 to m, you get sum of all m numbers as m into m plus 1 by 2. And then because I'm subtracting 1 plus 2 plus up to n, that will be subtracted here. So bring this term here, this n group n one side and m keep m other side. So you get, if you bring this and simplify, you get n square. So I want to find n and m such that n square is m into m plus 1 by 2. In other words, this number m into m plus 1 by 2, numbers of this form are called triangular numbers, and numbers of this form are called square numbers because it's square of some number. So I want to find numbers which are square as well as triangular, and such a numbers are very interesting in number theory. So this is square as well as triangular. So if you multiply by 4 on both sides, listen, you multiply by 4 on both sides, you get 4m square plus 4m, or 8, not 4, 8. You multiply by 8 on both sides, so you get 8n square. I'm multiplying by 8 on either side. So this is 8n square is equal to, this is 8 divided by 2. You get 4 remaining. So 4m square plus 4m. So upon multiplying by 8 on either side, you get 4m square plus 4m is equal to 8n square. Add 1 to both sides. So if you add 1 to both sides, you get 4m square plus 4m plus 1. That becomes 1. And bring this 8n square to the left hand side. You get minus 8n square. Now this I can write as 2m plus 1 the whole square, because if you expand this, you get a square becomes 4m square, 2ab terms becomes 4m, and b square terms becomes 1. So I can write this, simplify this equation to this form. And now if you assume x is 2m plus 1 and y is 2n, then this equation can be translated further into very nice equation like this: x square minus 2y square is equal to 1. So this particular equation with respect to n and m, where m is greater than n, is now transformed to a new equation of the form x square minus 2y square is equal to 1. So I want to find pair of numbers x comma y such that x square minus 2y square is 1. And Ramanujan knew how to solve this equation. In fact, the more general form of this kind is called Pell's equation, and which was actually not known to Ramanujan himself, but was known to the ancient mathematician Brahmagupta. To be correct historically, this kind of equations written in the form x square minus capital D into y square is equal to 1, or actually in the mathematical literature is called Pell's equation, but to be true, it should be called Brahmagupta equation, because Brahmagupta, the old ancient Indian mathematician, was the first one to provide the proper solution for this. He knew, he gave the methods to get recursive solution, and he solved this kind of problem completely for various values of D without how to sort to any algorithms. He gave wonderful formulas to find methods to solve successive solution, not only one solution, but he gave methods to find infinitely many solutions. But the way that Brahmagupta gave was different from how Ramanujan solved this. Even Ramanujan knew how to solve this kind of equations, but the way that Ramanujan solved was to handle what is a technique called continued fraction. So I will just explain how Ramanujan solved this. Okay. So the story actually goes like this. When the problem was posed to Ramanujan, he thought for a few minutes, maybe 1 minute or 2 minutes, and then told Mahalanobis, well, you note down my answer. He narrated the answer. Mahalanobis noted down the answer, and he was so surprised and shocked because how come Ramanujan could immediately guess a solution to this kind of very difficult problem, that too within few minutes, and he was working involved with other work in cooking, and he could still solve, effortlessly solve such a hard problem. And that is what is about Ramanujan's speciality. Now what, again, this is an incident where he was fortunate, Ramanujan was fortunate to hear a problem for which whose solution is already known to him. Even he has worked down this problem very clearly in his notebooks. He knew the solution for all these problems. So it so happened that Hardy gave a number 1729, which was already done by Ramanujan in his notebooks. Mahalanobis gave a puzzle whose solution turns out to be a, a case where Ramanujan knew the answer already. So it so happened that is why Ramanujan could immediately guess the answer and tell that. But to recall such thing, and because he could have done this in his notebook at a very early age, so because of the tremendous interest and passion that he had towards mathematics, Ramanujan could easily identify the problem with the known problem that he has already done and could immediately guess the answer. So even then it is not an easy task. So what you have to do, the technique of solving this kind of general equation is take square root of this coefficient, which is 2 here. Supposing if I have x square minus 5y square is 1, I could have taken square root of 5. So whatever number that is here, you take square root of that and try to express this as a continued fraction. So if you assume this root 2 as alpha, what you can do is add 1 and subtract 1. The purpose of adding and 1 and adding and subtracting 1 is I have to choose a number which is very close to this square root. The square root of 2 is very close to square root of 1, which is 1. So choose an integer such that which is very close to this value. So 1 is the integer, positive integer, which is very close to square root of 2. So I should add and subtract such a number which is very close to the given number. So 1 is a natural number or positive integer which is very close to this. In fact, 1 is a perfect square. So I have to choose a perfect square which is very close to this number. Remember, 1 is root 1. So 1 is square root of 1. Okay. Square root of 4 is 2. That is somewhat far than root 2. Okay. So I add and subtract 1. What I do is I wrote this 1 as it is and I reciprocal this. You make this reciprocal here. And if you multiply root 2 minus 1 times root 2 plus 1, the answer becomes 1. So upon multiplying these two, you get 1. So I can write 1 by root 2 minus 1 as square root of 2 plus 1. And so if you want to continue this, alpha becomes, listen, this is alpha here. So alpha is 1 plus 1 by 1 plus root 2. Root 2 plus 1 I rewrote as 1 plus root 2. Because alpha is square root of 2 here, I can write this as alpha again here. So what happened is alpha is 1 plus 1 by alpha is 1 plus 1 by 1 plus alpha. This is 1 plus 1 by, you replace alpha again here. So this alpha I have rewritten like this. For this alpha, I'm going to replace this again here. Same thing. Alpha is 1 plus 1 by 1 plus alpha. So this is that alpha. This alpha is replaced as 1 plus 1 by 1 plus alpha. So this 1 plus 1 will become 2. So 2 plus 1 by 1 plus alpha. Again replace this alpha as 1 plus 1 by alpha. 1 plus 1 becomes 2. So you get this kind of, if you replace one alpha continuously, what you get is you get something like this. Alpha is square root of 2. So I can replace square root of 2 as, I can write square root of 2 as 1 plus 1 by 2 plus 1 by 2 plus 1 by 2, so on and so forth up to infinity. So this is the continued fraction expansion of square root of 2. And remember, this square root of 2 is square root of this coefficient here. Okay. So just for an example, if you take 81 by 37, this is a rational number because it's an integer. Division of two integers where the denominator is non-zero is the rational number. So if I divide 81 upon 37, you get a continued fraction like this, but this is a finite continued fraction. In fact, for any rational number, the continued fraction will have only finitely many terms. Only if the number is an irrational number, the continued fraction will go up to infinitely many terms. So this is one way you can classify. The continued fraction expansions are used to classify rationals and irrationals. If the given number is an irrational number, the continued fraction will have infinitely many terms. Whereas if the given number is a rational number, it will stop at some place like this. Okay, so you can think about this later. Now coming back to the original problem, what Ramanujan did was he could have taken this solution for continued fraction expansion for root 2. You take 1, 1, that is 1 by 1. This is 1 and 1, so that is 1 by 1. Then 1 plus 1 by 2, which is 3 by 2. Then 1 plus 1 by 2 plus 1 by 2. The next step, 1 plus 1 by 2 plus 1 by 2. Up to this term. Okay, these are called convergents. This is first convergent. This is second convergent. Up to this 2. This is up, if you take up to this term, it's called third convergent. So 1 plus 1 by 2 plus 1 by 2. If you simplify this, you get 7 by 5. Up to third convergent, you get 17 by 12 and so on and so forth. I have written the answers for x comma y here. So interestingly, you find if you take alternate pairs 1 comma 1, 7 comma 5, 41 comma 29, 239 comma 169, they will form solution for x square minus 2y square is minus 1, because if you take x is 1 and y is 1 here, substitute here 1 minus 2 is minus 1. If you take x is 7, y is 5 and substitute here, 7 square is 49, 5 square is 25, 2 into 25 is 50, 49 minus 50 is minus 1. So they form solutions for this equation. Whereas if you take this alternate solution 3 comma 2, 17 comma 12, 99 comma 70, they will form solution to this. For the first case, if you take 3 and 2, you get 3 square. That's 9. 9 minus 2 square is 4, so 9 minus 8 is 1. So this is what we want to solve here. We want to find solution for x square minus 2y square is 1. So x comma y will turn out to be this answers. So if you know this answers here, if I know, for example, x is 3, y is 2, x is 2m plus 1. Remember, we made this substitution. X is 2m plus 1, y is 2n. So if you can substitute back, you can find m and n. So 2m plus 1 is 3, so m is 1. If 2n is 2, then n is 1. So m is 1, n is 1. This solution is what Mahalanobis found. He knew this answer, but there's nothing to do here. This is a very trivial case, which means there is only one house in the street. There's no house before it and after it. So it automatically satisfies that condition. Okay, there's only, this solution says there's only one house in the street, your house number is 1, which means there is no house before your house nor after that. But it is specifically given that the number of houses is between 50 and 500. So this solution won't be true. Okay, we take the next solution 17 and 12. 2m plus 1 is 17, so m becomes 8. 2n is 12, so n becomes 6. This is an interesting solution. This says that there are 8 houses in the street in which your house number is 6. If your house number is 6, then if you add the previous house numbers, that is, if you add 1 to 5, you get 15. And when you add the next two numbers, after 6, you get 7 and 8, that is also 15. So the sum of numbers before 6 is equal to sum of numbers after 6 up to 8. I hope you understand this. If you add numbers up to 1 to numbers before n, which is 6 here, if you add 1 to 5, you get 15. And if you add the next numbers after n, which are 7 up to m, which is 8. So if you add 7 and 8, you get 15. Similarly, if you take next solution, you get this. That means if you add from 1 to 34, what you get, that is, you get 595. That should be equal to 36 plus 37 up to 49. But here, even then, the solution is not satisfied, because the total number of houses is 49, but in the puzzle it is claimed that it is between 50 to 500. Okay, so the next solution gives the answer. Here the total number of houses is 288, giving you the house number is 204. In fact, if you add all the numbers before 204, you get 20,706. If you add after 204, which is 205 plus 206 up to 288, you get the same answer, 20706, 20,706. So this is actually the answer for the Strand magazine problem post Ramanujan. Ramanujan, because he knew the continued fraction solution for root 2, he could generate this answer within no time. Within few minutes, he could give this answer. So that is how he solved. So not only Ramanujan could guess the answer for this particular problem, but these are all infinitely many solutions to this equation. So he has given a continued fraction solution, which not only solved the given problem, but also gave a method for generating infinitely many solutions. As I told before, he was master in solving many solutions problem for a given single problem. So, in other words, for a single problem, if you seek one solution, normally people will do one particular solution. They'll be quite happy with producing one solution. But for genius like Ramanujan, he was not satisfied with just producing one solution. He could produce infinitely many solutions. Again, proving the fact that he was a man who knew infinity, because he could play with the infinitely many solutions. He would play with infinitely many radical signs. He would play with many infinite objects, like just like a toy where child used to play. So this kind of things was quite commonly featured. There's another problem that was posed to Ramanujan of similar kind, where Ramanujan solved by taking square root of 10. So because of want of time, I'm not going to do this. So he gave this continued fraction solution to that problem. This is square root of 10. Okay, and square root of 10 has this continued expansion problem. Term. So he could solve this because he knew this already. He could solve this immediately. And these are formulas uh, written by Ramanujan in his paper called Modular Equations and Approximations to Pi, where he have written so many formulas. And here, before I wind up this, I mean, he could have, we have added 3 and subtracted 3 because square root of 10 is very close to square root of 9, which is 3. So you have to choose a perfect square whose square root is very near to this number. Okay, so square root of 9 is very close to square root of 10, and root 9 is 3. So you have to add and subtract such a number and do the same process. So in one of this formulas, you could have written 30 formulas in this paper. In one of the formula, in the last formula that he wrote, this is how the pi value could come up. The last formula, if you translate this into normal notation that we know as of today, you get this. This gave pi value to 17.5 million digits accuracy. And this was verified only in the year 1985 by Bailey, the American mathematician. And they were quite staggered to note that, astonished in fact, to see how much decimal places, because no one before Ramanujan's time could give a formula for pi which can generate more than millions of places. But Ramanujan's formula gave not only million but 17.5 million digits accuracy. But for the record, as of today, we know pi value up to more than 30 trillion places. Trillion is 10 power 12, which is much more than what Ramanujan gave. But for any of such modern formulas that people were doing now, they always acknowledge they had the basic idea given from this paper by Ramanujan. Okay, so this kind of formulas were basic for other mathematicians of today's time to explore as many places of pi, decimal digits of pi as possible. Okay, now this is a very nice formula, which is one of my very liking. You take 2143 and divide by 22. 22, of course, you can remember because Ramanujan's day of birth. So take 2143 and divide by 22 and take the fourth root. That is, press 2 times square root in the calculator. The fourth root is twice square root. I mean, you can press to, if you cannot find fourth root in a usual calculator, press square root sign symbol twice. You get fourth root. You get this answer. So this gives pi value up to 6 or 8 places of accuracy. So very simple. You just divide 2143 by 22 and just take fourth root. You get 8 places of accuracy of pi. So this kind of simple formulas were done by Ramanujan, and Ramanujan wrote this kind of crazy formulas, and this is why the reason why probably people have not acknowledged Ramanujan very much. So he could have written 1 square plus 2 square plus 4 square is 0. How come sum of positive numbers become 0 or negative? People cannot understand what Ramanujan was writing, and they were reluctant to support him to pursue his higher studies initially. But later, fortunately for him, mathematicians like Hardy and Littlewood acknowledges this knowledge and the reason behind this kind of writing. Today, this kind of summation formulas are known after him as Ramanujan summation. There are several kinds of summation methods that various mathematicians has proposed in history. One of such summation method was proposed by Ramanujan, and that is called Ramanujan summation method. In that sense, this formula becomes true. In fact, if you take this formula, which is the basic recipe for Ramanujan summation, this formula is called the Ramanujan summation formula. So if you take this formula, then you can see why Ramanujan's results were true. But unfortunately, Ramanujan could not have written anything or given any clue about how he got these answers in his letters to others. That is the main problem. And other important work by Ramanujan was partitions, where he could have written one as simply one. So the number of way to write one is just one way. You can write 2 in two ways, either 2 or 1 plus 1. So the number of ways in writing 2 is 2. You can write 3 as simply 3, or 2 plus 1, or 1 plus 1 plus 1. So you can write 3 in 3 ways, you can write 4 in 5 ways, you can write 5 in 7 ways, 6 in 11 ways, 7 in 15 ways. People knew this right from Euler's time. People knew about partitions. The partitions were not introduced by Ramanujan. Many mathematicians like Euler, Jacobi, and so many great mathematicians had worked upon these partitions. But what was new about Ramanujan's contribution, which came as new idea to mathematicians, was this congruence identities. Ramanujan guessed that partition of the numbers of the form phi n plus 4 is divisible by 5, is a multiple of 5. So if I take this here, if we take partition of numbers like 4, which is 5, 9, which is 30, 14, which is 135, 19, which is 490, all these answers. So this numbers 4, 9, 14, 19 are numbers of the form phi n plus 4. Okay, they are all numbers of the form phi n plus 4. So if you take this answers here, this is the partition list for first 100 natural numbers. We take 4, which is 5, 9, which is 30. See, any number ending with 5 or 0 is divisible by 5. Ramanujan conjectured or claimed that partition of the numbers 4, 9, 14, 19, 24, 29 were all divisible by 5. As you can see, the answer is 5 here. This is 30. And this is, if you take 14, you get 135. If you take 19, you get 490. If you take 24, it's 15. So any number ending with 5 or 0 is divisible certainly by 5. This was certainly found to be true. Not only that, he also found that partitions of the form 7n plus 5 is divisible by 7. And you see this beautiful pattern here. I told you that not only Ramanujan's formulas in many cases were true, but you find some beautiful pattern behind that. This numbers 4, 5, 6 are consecutive natural numbers, and this numbers are consecutive prime numbers 5, 7, 11. And it so happened incidentally that this coefficient of n being the prime number is divisible by 5. So this numbers of this form, partition values of this numbers of this form is divisible by coefficient of n. So if we take 5n plus 4, it's divisible by 5. If we take 7n plus 5, the coefficient of n is 7, so it is divisible by 7. If we take 11n plus 6, the coefficient of n is 11, so that is divisible by 11, and so on and so forth. And the next step, he proceeded with Hardy to prove an asymptotic formula. See, the symbol is missing in the PowerPoint here. This is approximately. The box should be approximately symbol, approximately 1 by 4n times square root of 3 into e power k root n, as n is very large. So Ramanujan gave asymptotic formula for partition of numbers. This works perfectly when n is especially very large. Large in the sense more than 10,000s or 1 lakh or something like that. If n is very large, then the partition formula gave by Ramanujan works very well. And for this accomplishment, he was given FRS, Fellow of Royal Society. And Ramanujan claimed in his notebook that there are only 5 solutions to this problem. X square plus 7 is 2 power n. The 5 solutions claimed by Ramanujan was given by this, but he had not provided. He has claimed that these are the only 5 solutions and not anything more or anything less. There are exactly 5 solutions, but no proof was given by him. When mathematicians started working upon this proof of these 5 solutions, it took nearly more than 3 decades for him until Norwegian mathematician Nagel proved this, that there are only exactly 5 solutions to this problem. And these 2 identities are Roger Ramanujan identities. You see the symmetry here. The numerators are perfect squares here. Q power 1, Q 1, 4, 9. This is Q power 0 in that sense. So this is 0 square, 1 square, 2 square, 3 square. And if you take the denominator, 1 minus Q times, this is, you see, 1, 2, this is 1, 2, 3. So consecutive natural numbers. Here the numbers are in AP, the powers of this terms. This is called Q series formulas. Okay, so you see 1, 6, 11, 16. They are numbers in AP with common difference pi. Again, these are numbers like 4, 9, 14, 19, and so on. Again, numbers with common difference pi. The same thing happens here. Here the powers are numbers which are 2, 6. They are product of consecutive numbers. Like 2 is 1 times 2, 6 is 2 times 3, 12 is 3 times 4. And product of such consecutive numbers are called oblong numbers or rectangular numbers. So such thing, and you find again the same kind of pattern here. The denominator will have powers which are again arithmetic which forms AP with common difference pi, 2, 7, 12, 17 numbers with common difference pi, 3, 8, 13, 18 common difference pi. And this is Ramanujan's tau function, which was introduced by Ramanujan, not by anyone else. This was introduced newly by Ramanujan. And this particular inequality called tau conjecture was proved by uh, Perry Delling, for which he was awarded Fields Medal some 46 years after Ramanujan's demise. And these are the primary works that Ramanujan did. He concentrated and contributed so much to this 11 subdisciplines. And this was called the Waring's conjecture problem, for which, I mean, there are some problems which were solved extensively after Ramanujan's time. So I'm, because of the want of time, these are some applications of Ramanujan's work. These are the papers published by Ramanujan. Ramanujan published 30 papers on his own, and he published 7 papers on collaboration with Ramanujan. And Ramanujan's legacy, that is, we remember Ramanujan towards by his notebooks now, because almost all the problems in notebooks and contents of notebooks were solved by the efforts of two and several mathematicians, beginning with Bruce Bund, George Andrews, Ram Murthy, Kumar Murthy, and Ramchandra, and so many Indian mathematicians and other foreign mathematicians have been working, toiling very, very hard for the last 4 to 5 decades for proving all these results. They were published by Springer, which I will show in the last slide. And for publishing the paper, research paper, highly composite numbers, Ramanujan was given BA degree by research. I will show that to you. Now, when one of the known friends to me once asked me, why did Ramanujan was given a doctorate? Why was he not called Dr. Ramanujan? People like me, even now, today was called Dr. something, and more people are getting doctorate degrees now, even for producing a very small and insignificant result. But Ramanujan, in spite of producing such great theorems and formulas, churning out formulas, and having such a great knowledge, why could have been not been given degree like PhD? He was indeed given PhD degree by Cambridge University. See, the problem is Ramanujan died in the year 1920, and before 1920, even in countries like England, there were no universities offering PhD degree. The concept of PhD degrees came into existence even like countries like England only after 1920. So unfortunately, Ramanujan lived in an era where these degrees are insignificant. First thing, and second thing, after 1920, after some time, like around 1930s or so, Cambridge University gave this announcement that Ramanujan's anyone who has got a degree, research degree, like BSD, BA degree by research, or considered as equivalent to getting PhD. So in that sense, Ramanujan was indeed a PhD degree holder. But according to me, this kind of degrees are very, very simple and very normal thing for him. See, even if you offer one PhD degree for a single formula that you have written, he has written 3,872 theorems on his own. So nearly 4,000 PhD degrees can be offered for Ramanujan. And even as of now, the recent survey told us that there were only 875 universities in India, and even globally there would be around less than 5,000 universities. So the whole university, even the universities throughout the world, even if they offer one PhD per university, all the universities can give one degree to Ramanujan. So Ramanujan was such a person who were above all these degrees. He was an immortal person. Degrees and other things were not eligible to him. He was above everything, such thing. Only for mortals like us, such degrees have some value to us because it gives us promotion, gives us job, it gives us some salary or something like that. But people like Ramanujan never require such thing. This is a FRS degree given for his work on partition, I told you, and for other works in number theory. And this were the terms known about Ramanujan today. Ramanujan summation was one among them, which I told you. There is a concept of Ramanujan graph, Ramanujan tau function, which I discussed, Ramanujan prime. There's a prime called Ramanujan prime, Ramanujan's constant, Ramanujan's master theorem. This Ramanujan master theorem is collection of several beautiful integral formulas. If chance occurs, you can refer to his notebook. And again, Ramanujan, knowing this master theorem, he could tease his friends by giving special cases, as what he did in his nested radical problem. This is Ramanujan-Nagel equation, is what I showed you. X square plus 7 is 2 power n, where Nagel solved it. Hardy Ramanujan number is 1729 and all those things. There are several things that were known about Ramanujan as of today, because he had done so much of research. And to conclude this part, I will just go through some of the thing uh, that is circulating in internet so far. There was some many news about recently in WhatsApp circulating that 220 and 284, somehow doses of 220 excluding itself happens to be 284, and somehow doses of 284 adds up to 220. And this was given by Ramanujan. That is why Ramanujan was considered as a genius. This is completely false. Actually, this was given by Pythagoras in the 5th century BC, the BC time. So this was not credited to Ramanujan. If there are so much of things for which Ramanujan can be appreciated and celebrated for this original work like this, why should be Ramanujan can be celebrated for a thing which others discovered? So it is not true. And as mathematicians and people, we could not do that. As teachers of mathematics, we should be very, very careful before propagating or teaching such thing and spreading in, especially in social media, because social media is a very powerful medium which can be passed on to any part of the globe within few seconds. So we are, unless we are sure enough, we can't spread such thing. In fact, there's another common news that Ramanujan was responsible for producing formulas which work in ATM machines. If you go and put your credit card, debit card, you get all things that is required for transaction, for e-transactions and getting money from ATM machines. Ramanujan's formula is the only thing that is making it possible, which is again very, very untrue. Ramanujan's formula has nothing to do with ATM machines. The concept of ATM machines came only after 1970s. So it has, and Ramanujan died in the year 1920, and he could not have done all these things. In fact, Ramanujan produced all these wonderful formulas for the sake of enjoying mathematics and producing new results one after the other. He was never bothered, even could not have thought about applying this to other issues in life, apart from some mystical connections with, say, religious aspects or other things. He could not have done much in applying. He was a pure mathematician, and he did mathematics for its own sake, not for bothering much about in what sense it is getting applied. And this man was portrayed as Ramanujan. He was actually Srinivasa Varadan. Even in many newspapers, it was claimed this is Srinivasa Ramanujan, a self-taught mathematician. It was untrue. This was some other man. This photograph is not about Ramanujan, and many sources claim that this was father and mother of Ramanujan. This is Ramanujan. The very joking thing is Ramanujan could have never looked like this. This is some other person, and this is S.R. Ranganathan, the man who wrote the first biography of Ramanujan. So this is something quite a very, very different picture, not at all related to Ramanujan. In fact, there's no picture that we have obtained about Ramanujan's father. Ramanujan's father, no one knows how he looked like. There's no picture available about him at all. But unfortunately, people were spreading these false pictures and false news about him. And again, another false news about Ramanujan. This was Ramanujan and his wife. This was again a false news. This has to be avoided. This is actually A.K. Ramanujan, the English poet, the very famous English poet, and his wife. Probably, I think so. So I'm not sure about even that, but this is definitely not Ramanujan. And this was the compilation of notebooks done by other great people like Bruce Bond, George Andrews, which contain original proofs of the formulas in Ramanujan's notebook. And this was by Ramurthy and Kumar Murthy. This is by Alladi Krishnaswamy. So these were some of the very good sources that you can look for Ramanujan's mathematics. So I thank very much for this wonderful opportunity given to me. I hope I had finished in time and not taken much of your thing. If there are any questions, I'd be happy to answer. Hello? Hello? Any questions? Do you hear me? Hello? Hello? Sir, any questions? I think I can stop presenting my file. So if there are questions I can answer, I'll be happy to answer. Otherwise, we can wind up the program.
Sir, can you hear me, sir?
Yes, certainly. I'm hearing you.
Yeah,
I
thank
have
you very
short.
much
Yeah.
for your insightful talk on the works of Ramanujan. Now, I would invite students to ask any questions or queries if they have.
Stand there, stand there.
Good afternoon, sir. This is Kamal Kumar Pandyan, student of MBTs. Sir, I wanted to ask that can you give some ideas based on the projects that you wanted to do on Ramanujan?
I can't hear what you're saying. Can one of you could translate?
Sir is asking the question related to can you give any projects related to the Ramanujan? So, what kind of work can be done related to the Ramanujan? So, is
See,
that
as I told you, there are many conditional identities that you can find in Ramanujan's notebooks. So probably you can pick some of the identities that Ramanujan wrote in his notebooks and then work upon it. You can probably find a similar identity as what Ramanujan did, or you can extend that identity to the next level. Okay, that is always a scope for working on Ramanujan's area. And again, there are some integrals that you find in Ramanujan's notebooks. You can find try to evaluate similar results as how Ramanujan did by changing the parameters. So that can be done, but you have to have very much hard work and patience to do that. It cannot come in 1 or 2 days to you. You have to understand the problem cleanly and then work upon it. Only then you can get all those results. The results are very beautiful, but they're very deep. They're not elemental.
sure, sir? Can you give us any suggestion books, sir, for the student point of view? So, what
Uh,
you
so
can
I,
bring?
I gave actually there's a wonderful little book by what is called Spirit of Ramanujan, written by Bruce Bund. It's a very little book containing so much of elementary ideas by Ramanujan. And there is another 3-volume book, small book, especially useful for young students, uh, undergoing high school, higher secondary school, and college students doing their undergraduate programs like yours. It was published by AMTI, written by my mentor, Sri P.K. Srinivasan. I can suggest that book to you. I can send a mail to you. You can purchase online from their cart. I will send the details about that.
Thank you, sir.
Okay.
Any other question? Any other question? Anybody else? Come forward. Do you have any questions? Speak, speak, speak.
Good afternoon, sir. My name is Akash and I am from PSC, NPC. So my question is, what is a radical and how do you solve a series which has radical in it?
See, radical, as you know, is a symbol which actually specifies like square root or cube root or in general nth root of a number. So if you apply radical sign to a number, especially to a positive real number, the answer will not be a rational number. It converts a number into irrational form. Like if you apply square root radical sign to a number like 2, you get square root of 2. That makes it irrational. So it kind of entities which gives irrational numbers to you. If you want to find the generate irrational numbers, the best way is to take radical signs.
Yes, sir. Thank you, sir.
Anybody else? Come forward.
Good afternoon, sir. This is Rihanna from the LBCS. My question is, which areas in mathematics area is helpful for us to do research work?
For your own sake, for working.
Yes.
See, there are several branches of mathematics that you can work upon. The main part of that mathematicians today are working there in graph theory, fuzzy mathematics, fuzzy logic, and you can take anything and attach fuzzy to it. Like analysis is fuzzy analysis, topology is fuzzy topology. And you can apply fuzzy to anything. So fuzzy mathematics is one thing, and this kind of mathematical research are very much done by many people as of today. It's a large scale uh, research done. It's very easy also. So to those who want to pursue and do research in a short span of time, they can either do in graph theory or in operations research, or in fuzzy. Even you can apply fuzzy to operations research. Like you can talk about fuzzy transportation problem, you can talk about fuzzy assignment problem and all those things. You have done that in your UG classes. But what you can do is assign fuzziness to it and do some research and come up with a method which can help you to get the optimum solution. So that's kind of possible. It is quite easy actually. But if you want to do deep research, you can take analysis, algebra. So this kind of research are very deep research. Even for knowing what, you have to spend nearly 1.5 years of study to know what is done so far and what you have to do. So you have to spend quite a number of years in doing in number theory or in algebra. Like there is a topic in algebra, Lie algebra, or algebraic geometry, for example. These are very deep areas where you can work very hardly, but it will consume more time. But if you want to spend very little time, you can probably take ODEs, differential equations, and assign some programs. If you are very good in computers, you can make some computer programming. Like you can use Maple MATLAB software and construct an algorithm for which you can take a situation and construct a mathematical model for it and solve the model through that algorithms and give the solution visually using that software. That was done by many people through as of now. These areas were very active now.
Thank you, sir.
Next student wants to ask some questions, sir.
Good morning, sir. This is Kamal Kumar Padhyay of MPCS, BSc MPCS. Sir, I wanted to ask that how did Ramanujan got the ideas to solve any problem in few seconds, sir? Or we can say that he solves any problem very easily, sir. Then how he would get the idea for doing that?
No one was clear. Even I'm not clear about it. It was still a mystery. If you ask any mathematician working on Ramanujan's area, probably they could not have the right answer for this. It still remains a mystery how Ramanujan thought about those things and how he created that many problems and could solve effortlessly many hard problems. He would say that it was because of Lord Namagiri Tayar's blessings, but it is not true. But one thing is sure that he was doing very much hard work. In spite of having his genius brain, he was toiling day and night to realize his genius. So one thing that we should learn is even if you have good brain, you have to work hard. That's a lesson that you have to learn. But I'm not sure about how he has done it. It still remains a mystery.
Thank you, sir.
Thank you very much, sir, for answering all the queries.
What will I do? I answer. That is all.
Thank you, sir. Now I invite.
Two words before I wind up, madam. Before you give your vote of thanks, this is I think third or fourth time that I'm addressing LFDC.
Yes.
Since I came to the last year January, I was there for the whole day on 25th of January, the day before Republic Day. If you remember, I remember all days and events, so no problem for me. Because I was always indebted with numbers. So I was very happy to be there because all the staff members and the whole management were very cordial and they were very sincere in organizing such events to motivate young students like you. So you should take this opportunity to learn more and make use of the chances given to you, not only by people like me, but from other persons also who are addressing to you. So my congratulations to the department and the faculty members and the management for organizing such wonderful events and giving the real chance for students to know many things. So my congratulations to them. Thank you.
Thank you for those kind words, sir, and bless our students to do more in whatever area they are interested.
Certainly, if you want any help from my side, I can always suggest. If I know myself, I will teach you. I don't. If you ask me from a thing that which I do not know, I may relegate you to a person who's an expert in that area. So I can always do that. If you want any help, and my sincere blessings and my prayers to Ramanujan for you. I will do that.
Thank you, sir. Now I request Mrs. Uma from the Department of Mathematics to propose vote of thanks.
Good afternoon, sir, and good afternoon, everyone. It gives me an immense pleasure to deliver the vote of thanks for this session on glimpse of great mathematician Srinivasa Ramanujan. I take it as my pleasure to express our gratitude for today's resource person, Dr. Shivaraman sir, gives us insights into the topics of glimpses of great mathematician Srinivasa Ramanujan. And sir explained the Ramanujan mathematics in an early age of Ramanujan. How he is thinking, how he is passionate about the mathematics, and he will give the answers for the questions of root x plus root x plus y is equal to 7 and x plus root y is equal to 9 in 1 second. And sir explained the magic of numbers, and those are used in the form of square matrices, and it is called as the matrix square. And sir explained the importance of 27 in astrology in the point of Ramanujan, and sir explains very beautifully about the marks in Ramanujan's formulas, and he shared some incidents which had happened at England, and sir gives more information about the Ramanujan, how he solved the solutions, and he will give them many methods to solve the many questions in very few minutes. That is nothing but 2 seconds. So thank you, sir. Thank you very much. We are lucky to have to know about the Ramanujan, and I thank our college management principal, Reverend Brother Vincent Reddy, and Vice Principal, Mrs. Jayanti Reddy, for encouraging us and giving constant support for organizing this wonderful session. Thank you, one and all.
Okay, so Ramanujan, let Ramanujan bless every one of you. Try to learn mathematics in a more enjoyable way. Okay, so thanks for this opportunity.
Thank you, sir.
Thank you, sir, Shivaraman, sir. Am I audible, sir? Are you able to hear me, sir? Yeah, good afternoon to one and all. Small announcement for all first year students, BSc, MPCS, MECS, and MSCS. So already Naveen sir and Uma ma'am informed you. Sir, Shivaraman sir. Sir, are you there? Can you hear us, sir?